All right, so now let's talk about why we're doing what we're doing. This is, our objective here when working with these matrices is to find the solution to a system of equations, right? This is supposed to be kind of a shortcut way to find solutions to our systems of equations. And so to do that within a matrix, we can either use Gaussian elimination, okay? Or we can use we can take it even a step farther if we wanted to and use what's called Gauss-Jordan elimination. Sometimes it's called Gauss-Jordan reduction. But what we want to get is our matrix to be what is called row echelon form and reduced row echelon form. Okay? So we're going to call row echelon form, okay? Or if we're doing Gauss-Jordan elimination, we want reduced row echelon form. Let's talk about what in the world that means, okay? Back on this example way over here, scrolling, that I've already marked up like crazy. Let me clean this up a little bit. This matrix on number 18 is in row echelon form. And the only reason it's in row echelon form is two things. We have leading ones in all the rows. That means the first number you see as you read the line as you would a line in a book from left to right is you see ones, leading ones, with a triangular array of zeros down below. Okay, we get pretty fired up about that because once we have it in that form, we can then say, well, z would be 2, and then we would use some back substitution like we did here to get the other values. What is x? What is y? We know z is 2. Okay, so that's going to be our objective. We're going to, on purpose, use our elementary row operations to get our matrices in what is called row echelon form, okay? Any rows consisting entirely of zeros is moved to the bottom of the matrix. That's just a little organization thing you need to do. If you have a row entirely of zeros, move it to the bottom. You can interchange rows, right? Okay? It says for all other rows that aren't all zeros, for any other rows, the first non-zero entry is 1. This is called the leading one. The leading one in each non-zero row is to the right of the leading one in the row immediately above. Get them organized like that. Okay? So a matrix is in reduced row echelon form if it is not only in row echelon form, but also each row with the leading entry of 1 has zeros above the leading one. Let me show you some examples of row echelon form. See, leading 1, a 0 down here, okay? Leading 1, zeros down here, okay? Leading 1. Here's a row consisting of entirely of zeros, and it's at the bottom, okay? We've got zeros below the leading ones. Okay? Now, in reduced row echelon form, that is when not only do you have a leading one, 0 below the leading one, you also have a 0 above the leading one. I'm trying to draw a good shape around that. Okay? So you did that as well. So here, this is not only in row echelon form, okay? It is also in reduced row echelon form because of the zeros above. Okay, and I love this form because I'm telling you right now, you can look at this and see what the solutions are, okay? X is 150. Y is negative 85, and Z is 12. Done. Okay? It takes some doing to get it there, but that's good. Okay? On this one, leading 1, leading 1. This is in row echelon form. That was an arrow, not a minus sign. Okay? And with this leading 1, we also had a 0 above. Okay? So that is reduced row echelon form. And this is kind of strange when you have something like this. Okay? When something like that happens, when you have a row of zeros, you are going to have a solution to that equation. And actually, you're going to have to involve a parameter to express those solutions to equations. On something like this, I would say, okay, z, which z doesn't have a leading 1 that corresponds to it. Z is going to be some value at all. Okay, any value you want. A lot of times we use a t for our parameter. Okay, where t is any real. So t is an element of any real numbers. Then you would use some back substitution to find what y is. Okay? Now this equation here says y is equal to negative 3z, not y is equal to, y minus 3z is equal to negative 4. Now if you solve for y is going to be equal to negative 4 plus 3z. But don't write a z, write what, I said don't write a z and then I'm writing a z. Write what z is equal to here. T. Okay? And then you can say this equation in, written out would be x, 1x, plus 0y plus 2z equals 25. Right? Okay, and so solving for x, you would get x is equal to 25 minus 2z, which z again is still just t. I can't train my pencil to just write t instead of z. This is what you consider to be your solution set if you get a row of zeros. That's how you would need to tackle that using these parameter values for t. So actually, depending on what t is equal to, you can let t be equal to anything. You're going to get an infinite number of x, y, z ordered triples that would satisfy this equation as long as it went by the rules here that you defined. Okay? So let's see what's next. Here we're going to actually talk about what does it mean to find the system of equations by using the method of Gaussian elimination. You're going to first of all write the augmented matrix for the system. That's a pretty easy thing to do. Okay? Just put it in matrix form. The second thing is we're going to use elementary row operations to write the augmented matrix in row echelon form. Just get those zeros at the bottom in row echelon form like it shows down here. Okay? Then once you have that, you should be able to see what z is going to be. Z is going to be equal to that, whatever number that is. And then you use back substitution to solve for the rest of them. Okay? Now, it says when writing an augmented matrix in row echelon form, the goal is to make the elements along the main diagonal here highlighted in yellow. Okay? You want to make this main diagonal elements, see how it's diagonal, that's called the main diagonal elements, be 1. And then everything else below that, to the lower and right, or sorry, to the lower and the left, you want those to be zeros. Basically, that's what it looks like for something to be in row echelon form. I don't know if it's good to pause right here. Yeah, I'm going to go ahead and pause right here, and we'll do example 3 in the next video. I don't think I have enough time to do it right now. Okay? But we're going to use Gaussian elimination to find the solutions to this system.